Barry is a chartered engineer with a BSc in physics and over 30 years experience in software engineering. As a developer and designer, he has worked on projects including radar tracking systems and OLVIC control system. He progressed into project management and consultancy roles, including managing large projects such as underground train monitoring system and a network voice mail system. He then spent over 10 years as an operations manager and later divisional director for one of the UK's largest independent software houses, IPL, and overseeing projects for clients including a medical device company and a major.
Okay, I'm going to provide a very brief introduction to software coverage today. So we're talking about coverage and coverage metrics for software testing, and I'm going to talk a little bit about structural coverage metrics at a very, very lightweight level with diagrams. So it's like a blagger's guide, if you will. So coverage, software coverage, is really a map of where you've been. It's a map of what you've tested. So it's a means of knowing where you've been, what you've looked at, and much more importantly, what you haven't looked at. And it's usually expressed as a percentage. So people set targets of percentages for coverage, but there are various different types of coverage. And not all coverage, as you would expect, is created equal. Some are more useful than others. 100% of one may actually not, almost certainly will not be 100% of another. So testing and coverage refers to dynamic testing as opposed to static testing. Static testing has got a lot of benefits and a lot of values, but that's not what I'm talking about, but somebody will be soon. I'm talking about actually executing the code and having something measure where you've been, what you've done, and by implication what you haven't done. Typically expressed as a percentage, so we'll have some sort of thing that we're measuring, like number of statements. So you'll have a total number of statements and a number that you've actually executed in the test, and that's your coverage metric as a percentage executed over total percentage. Obviously 100% is a nice idea, and in many cases that's what we'd aim for, but obviously it's not realistic at system level. It's rare that you would be able to do absolutely everything at system level and get 100% of a realistic metric. However, it is much more realistic to do so when you're actually testing your components and you're doing your lower level tests, your unit tests. So, why would you care? Maybe you don't, maybe it's just a day out, and that's fine. But you probably care because we're all interested in having software that works properly and does what it's supposed to do. And we're about eliminating the risks of it doing something wrong, and that could be risks to safety, but perhaps not equally important, but also important is risks to reputation. If you, it's obvious if you have a plane that we want it right, but if you're a bank, it's perhaps less obvious. It's not the end of the world if it goes wrong, but it might actually be the end of your business. If your customers see it go wrong, they might migrate to somewhere else. So most people that develop software, pretty much anything upwards of an app on a mobile phone, and much beyond that, and you're going to want to know that you've got a reliable system, and that means being thoroughly tested. So we really want to show the software is fit for purpose. We want to actually do this hierarchically, as was described previously. We want to look at components and build up a picture of what we've actually done. And there can be lots and lots of components. This is somewhat superseded by the example of a jet engine, which is rather more exciting. But would you want to drive your car if the indicators had been tested but nobody bothered to test the brakes? I certainly wouldn't. Hopefully you wouldn't either. So coverage helps us to know what has been tested and make sure that we've checked everything that needs to be. And at some point, if it's a significant software system, pretty much everything needs to have been checked at some stage. All of the components, all of the bits that go to make up the system, just as was talked about previously, needs to actually be verified and tested so that we can show that they're all working and that they're all working together. Any little piece can fail. And in a software system, the smallest, most trivial things, literally a typing error, can make a huge difference. And it can be an error that wouldn't be picked up by static analysis. This example obviously isn't software, but it only takes one O-ring to take the whole system down. Now, that may seem slightly frivolous, and I use this one because, well, A, it's quite interesting, and B, I had a picture of it. But whilst that was a hardware failure, the early Ariane mission exploded purely due to a runtime error on the software. So it does happen. Thankfully, Ariane wasn't manned, nor was the Beagle. The Beagle also failed due to a software error, although slightly more of a design error rather than a testing error. It failed to different teams having used different units for passing one of the data items across an interface. So there are various types of metric that tell us a bit about how much we've done, how much of the software we actually covered. It's not just one type of thing. There are lots of different things. I'm not going to talk about all of them, but I am going to take you through a little tour of a few of them, of the ones that measure how much we've been through the structure of our software. And they have differing thoroughness, as you'd expect. So I'm going to use a very simple code example. I suspect that a number of you either are or more likely at some point in your career were programmers. So this is going to be very trivial, especially for those that weren't. So I'm thinking of a simple function. I'm imagining a function that has a simple logical decision in it. So here's our decision point, and it's got one route through it here. And I'll draw a diagram of that as well, frankly, because that just makes it easier to describe what's going on. Just a simple logic flow representation of the code above. So the first metric that we might talk about is function coverage. And really, function coverage isn't a great deal of use at unit testing or component testing level, more useful at system level, where we can, because all function coverage really says is the function's being called. And that really doesn't tell us anything useful because it doesn't tell us what's gone on inside. But in terms of systems, this might be useful because we can actually look at how much has been measured. The problem with this, of course, is it really doesn't do very much. There's plenty of stuff that's missed. So we move on to a more common one, statement coverage. Statement coverage says, well, look, if we look at the code, there are a number of executable statements there. Let's make sure that we've been through all of them. That's a good start. So there's a test path that takes us through all those statements, passing in 2 parameters and going down there. But I think you can see the obvious problem. It doesn't actually go all the routes. Not everything is tested, but all the statements are tested. So null statements, null branches, for instance, are very easily missed by this. Nevertheless, this is the commonest coverage metric that you'll come across, and it's certainly a damn sight better than nothing, because if you're going through every statement, well, you've not done everything, but you've done quite a lot. But we can build on that. We can go to what's called branch coverage, and there are interchangeable names for some of these. I'm going to use the ones that I like. Your mileage may vary, particularly yours, Steve. Branch coverage is about making sure that where there's some sort of decision here, and here's my decision, that we've been through both branches out of that decision. So each branch is executed at least once. So here's a test with a parameter where P1 is 1, which will drive us down one route, and there's another one where P1 is 0, which will drive us down the other route. So we've now got 100% coverage of our branches. There is a catch, however. There are more test cases than there were in the simple statement coverage, but that's good because we're getting higher confidence. But we're not actually testing everything. All I've done is vary P1 here. So issues with P2, P2 is always 1, so I've not tested the other case of P2. So again, better, but still not perfect. Another type of coverage is called condition coverage. Condition coverage is all about looking at the individual components, the Boolean components. So there's one and there's the other. These are 2 Boolean expressions. P1 can either be greater than 0 or not, so that can be true or false. Likewise, this one, P2, could be greater than 0 or not. So again, true or false. And we make sure, to achieve 100% condition coverage, we make sure that each of those conditions has been in each state. So each of those has got to evaluate true and false. So I'll split this out, this flowchart, to just give a bit more detail, just so that we can see a little bit more what's going on. So I've taken that one decision and shown its components. So there's our first test, where P1 is true, but P2 is false. And then we get another test, where P1 is false and P2 is true. So we've tested true and false for each decision. That's good in terms of testing the decision, but the obvious flaw here is we still haven't necessarily tested all the branches. Clearly, you might choose to pick values that did some of that for you. But if you're looking at bulk, where a test tool is measuring the coverage for you, then it could tell you 100%, but there could still be stuff that you haven't. So we can go a step further, and our step further has a variety of names, but I'm going to call it condition decision coverage, one of the more common names for it. And this is really a combination of the two that we've previously talked about. This is condition and branch. So again, we'll drive one test where we go down this path with P1 is 1, and another test where we go down that path, but we'll now have a third test to drive us down the other path. That's actually pretty good because we've been through all values of all the conditions. Both of these conditions have been tested true and false. We've been down both branches. Not a bad starting point. There is, however, a catch. I've picked fairly sensible examples, but even though all conditions are tested and all branches are tested, it's not necessarily going to get us everywhere. So I'll take a slightly more complicated example with 3 Boolean values. Each one of these, A, B, and C, is something like P1 greater than 0. So I can define a set of tests that have A, B, and C each taking both values, so it tests all the conditions, and it goes down branches 1 and 2. So there we go. First test, A, B, and C are all true. Second test, A, B, and C are all false. All conditions have been true and false. Both branches, branch 1 and branch 2, have been executed, but I think you'll agree it's still not a very good test. So that brings us to modified condition decision coverage, and that's the same, except that we have to show that each of our A, B, and C conditions can independently affect the outcome. So to take you through that very quickly, we'll look at a slightly same example, and I'll give it a diagram this time as well, just so that we can see what's going on. First of all, I vary A, keeping B and C the same. So I'll do a true and a false test for A. And so we can see that we're varying A and only A and going through branch 1 and branch 2. I then do the same, vary B, true and false, leave the other branches the same. I'll then vary C, again leaving the other branches the same, and again go through both branch 1 and branch 2. That's actually very rigorous. The downside is it's more tests, but it's not as many more as you think, because some of those, if you pick your test data carefully, some of those are actually duplicates. So there's actually only a set of 4 tests there. So there's our 4 tests. More complicated than condition decision coverage alone, but more rigorous. You can go a step further. This is particularly required in most safety-related and critical systems. You can go further. You can test all possible combinations of A, B, and C. That's generally called multiple condition coverage. Obviously, it's quite rigorous, but it's a lot more work, and arguably the additional work is not worth the benefit. There are lots of others, which in deference to the time, I'm not going to talk about. Loop coverage is about counting the iterations around loops. Entry-exit coverage is a more enhanced function coverage. Parameter values are about making sure that each parameter has been through its possible ranges of values, like an integer would be 0, positive, maximum positive, negative, and maximum negative, that sort of thing. State coverage specific to finite state machines, and linear code sequence and jump is quite complicated, quite rigorous, but much more difficult to do and to automate. So all coverage measurement involves modifying code so that it reports what's going on when you execute the test. And you need to remember that. You could achieve that by instrumenting your own code. You used to do it in the old days, but for anything, typically with conditional compilation, but for anything larger, this becomes quite burdensome in terms of the amount of work. So you tend to use a test tool, of which there are many. G-COV's worth mentioning, just because it doesn't do very much, but it is free, which I find people are always quite enthusiastic about. The market type leaders, tools like Cantata, LDMS, Parasoft, Vectorcast, all these will do this sort of thing. I mentioned Squish not because it is particularly relevant, I just really like the name. So use a test tool, and remember, if you're using a test tool, then you can actually rerun the tests without the instrumentation, so that you're testing the actual code rather than the instrumented code. So run first with instrumentation and second without. How much coverage should you aim for? It sort of depends on your system. Some things will need a lot, some things will need less, maybe. Critical systems, safety and so on, need a lot. business systems perhaps need less, but actually, do they really need less? Do you actually care less about something that you're putting in front of your customer? I suspect a lot of the time you probably want a higher level of coverage than you think. So set yourself a project target that's appropriate for your project, both for component level and for system level. 100% is nice and easy, but which coverage? Is it MCDC or is it function coverage? There's a big difference between them. So you want to know what you're aiming for and which one you're going for 100% of. Remember that if you set a lower target, you don't know which bit. 80% coverage means 20% not covered, and you don't necessarily know what hasn't been tested. So I would argue that it's always better to aim for 100% of something. A good default at component testing is to aim for 100% MCDC. It's quite rigorous, but to be honest, it's not actually that much harder to do than ordinary condition decision coverage. If you've done component level, then you can aim slightly lower at system level. Perhaps you just want to aim for 100% entry-exit coverage because you know all the bits work, so you're just checking that you can connect them together. I'll skip over that. Finally, then you measure your coverage using your automated tool. You look at the results. There may be reasons why your results aren't 100%. There could be a bit of code that deals with some hardware issue that it's impossible to simulate during software testing. But in general, it just means you've got something wrong, so you can go back and add tests if needed. But the coverage will tell you how much extra you need to add. Some tools will actually suggest test frameworks to do the extra coverage for you, which is quite handy. So to summarize, software coverage maps where we've been, what we've tested, and what we haven't, and it helps to show that the software is fit for what we're going to do with it. There are various types of structural coverage, which I've flown over. Modified condition decision coverage, MCDC, is one that's already been mentioned today and is generally accepted as a pretty good starting point. All coverage analysis involves instrumenting code, so you need to run it without the instrumentation as well, and there are plenty of test tools that support this. Set targets that are appropriate to your system, usually 100% of something. Thank you.
Thank you, Barry. Any questions?
Yeah, you don't have to instrument the code to measure coverage. My company, Vericell, sells a tool called Vericode that measures coverage running on the target hardware without instrumenting the code.
Using a hardware analyzer?
We use hardware to read the instructions executed by the target.
Yeah, fair comment.
And then we relate back.
So you actually look at the locations that have physically been accessed by the processor and map that back to a map of where the software exists.
Yes.
Yeah, fair enough. That is another way of doing it.
So my question, I guess, is tested the right word here? Because doesn't coverage tell you what's been exercised rather than what's been done correctly?
Yes, your tests still have to test what you want to know, but this is actually giving you confidence that it's more about what have we missed. So measuring coverage, it isn't a substitute for testing. It's something you do with testing so that you know how much testing you've actually done. Have you reached all of the little bits? Have you covered all the error conditions? Have you checked that final O-ring?
So
I guess the follow-on question from that then is, how do you know that the tests or your checks have actually checked the right thing?
Well, that is quite an interesting question, and I could spend about an hour on it quite easily. But you don't from coverage. You still have to do sensible tests. But if you're doing something like MCDC, then you've pretty well been through all of the combinations that your code allow. So there must be a test in there that's testing what it does. There's nothing much left. So you've tested everything. It doesn't mean your test was sensible in real world terms, but assuming your software was designed to do something, then if you've got that level of coverage, you know you've been through everything that you made it do. It doesn't test that what you've designed is sensible. That's a design verification. But it's not a be-all. It's a supplement to testing. So I skipped over the planning for testing. You do need to plan your own tests so that you've got a sensible set of tests and then see if that achieves coverage. Coverage is not of itself the thing you're aiming for, the only thing you're aiming for. You're aiming for sensible tests that test that your system does what you intended to do, and at the same time you're aiming to build up enough coverage to know that you've been everywhere and you haven't forgotten anything or left anything out.